Hey everybody, Dr. A here, and in this example, we are going to be exploring a statically indeterminate bar that is subject to thermal effects. So just like all of our other videos, you want to write everything down. Remember, this is not a spectator sport. You need to write this down and take notes so you fully understand what's going on. So let's get started. In the given information, we're being told that a titanium alloy bar is subject to a temperature increase of 55 degrees Fahrenheit. And then we're being asked to compute the stress due to thermal effects. We're given a modulus of elasticity of the bar material as 17,400 KSI, and we're given a coefficient of thermal expansion of alpha equals 5.2 times 10 to the minus 6, 1 over degrees Fahrenheit. We see a side view of the bar that's 18 inches long, and we see that it is fixed at both ends, A and B. And we see that the cross section is given here as 2 inches by 1 inch. So let's go ahead and get started. I'm going to start by writing solution. And the first thing I want to note is that this is statically indeterminate due to geometric constraints. So let's write this down. This system is statically indeterminate due to geometric constraints. So what that means is both of the ends of this bar are fixed. So that is providing us a geometric constraint that's going to cause us to develop additional reaction forces in addition to the applicable equilibrium equations that we have available to us. So let's go ahead and to help visualize that, we're going to draw a free body diagram of the system. So I'm going to write FBD of the system. And so in this free body diagram, I'm going to go ahead and redraw the bar. And I'm going to go ahead and draw the 18-inch length. So we can write L equals 18 inches. Now, at these two fixed connections, you have to ask yourself what happens here. Well, if this is axially loaded, then that means that we're not going to consider shear effects or bending moment effects. We're only going to consider axial reactions, and those are going to be reactions that are directed along the longitudinal axis of the bar. So I'm going to go ahead and I'm going to assume that I'm going to have an FA pointing to the right here, and I'm going to have an FB pointing to the left here. Now, assuming a compressive reaction effect is a very reasonable assumption here, because if you think about the behavior of the material, whenever we have an increase in temperature, in this case of 55 degrees Fahrenheit, what's going to happen is this material, the titanium alloy material, is going to want to expand. And when it wants to expand, it's going to want to push against the fixed connections at A and B. And as a response to that, we're going to develop axial reactions, FA and FB, that push back and cause a compressive force at both A and B, okay? So again, the material expands and wants to push outwards, and then in response to that, the reactions are going to push back, causing a compressive effect. So just by looking at this free body diagram, our equilibrium equation is going to be sum of the forces in the x direction equals 0, and we can write here FA minus FB equals 0. So clearly from here, FA is going to equal FB, all right? And again, it's going to be assumed to be a compressive effect, which is a very safe assumption given that we're going to have a temperature increase, which causes the material to want to expand. Now, since FA is equal to FB, let's call it F. All right, so since, again, this reaction FA is equal to, it's the same as FB, we can just drop the subscripts and call both of them F. So the load displacement relationship due to F is going to be our famous FL over AE relationship. So let's go ahead and write that down. Our load displacement relation is delta, and I'm going to call it delta sub F because it's due to the reaction force F, and I'm going to say that's equal to FL over AE. And we're going to pause right there for just a second. So again, that's our load displacement relationship, and that's going to cause a compressive effect, of course. All right. Now, because it's a compressive effect, we can add in a negative sign. So we can rewrite this as delta F equals negative FL over AE. Again, that negative that I just tacked on there accounts for the fact that this reaction force at either end, A and B, is causing a compressive effect. Now we have to remind ourselves that this is all due to the thermal effects, right? So we're going to say from thermal effects, we know that the thermal deformation of the thermal axial deformation is equal to alpha delta T times L, okay, where delta T is our change in temperature. And again, that's causing the material to want to expand. So what are we going to do? Well, we're going to set up our compatibility equation, and I'm going to say our compatibility equation is going to be the deformation due to the reaction force at either end, delta F, combined with or superimposed with the thermal deformation, delta T. And because it's a fixed rod, point A and point B cannot displace relative to one another, so that's going to be equal to 0. So now what I can do is I can use those two terms, those two equations, and substitute them into my compatibility equation. So delta F is going to be negative FL over AE. And then I'm going to say that's plus alpha delta T L all equals 0. And so remember, ultimately the problem asked us for the stress due to the thermal effects. So in order to get the stress, we need to solve for this force F, and then we'll just divide that force F by the cross-section area, okay? Another thing you can do is you can just solve for F over A, because F over A in and of itself is the stress due to the thermal effects. So you could do that as well. I'm going to go ahead and solve for F alone because you may encounter a problem where it only asks for the force F. So I want you to see how we can get F alone, and then we'll just go back and divide that by the cross-section area to get stress. So we can simply rearrange this equation, this compatibility equation, and we can get F equals AE times alpha times delta T times L divided by L. Let me draw a better division bar there, better fraction, all divided by L. So when we do that, all we did was we algebraically rearranged this equation to solve for F, and we see that the L's clearly cancel, and so we get a nice little compact formula for F is equal to AE alpha delta T, and from here we can substitute our values in. Our cross-section area, it was 2 inches by 1 inch, so that's obviously a rectangle, so that's 2 square inches times 17,400 KSI, that's the modulus of elasticity that was given in the problem statement, times 5.2 times 10 to the minus 6, 1 over degrees Fahrenheit. Let's be proper with our brackets here, and then times 55 degrees Fahrenheit. So when we substitute all this in and punch it through our calculators, we get about 9.95 kips. And again, you want to track your units here. You should be able to see that the 1 over degrees Fahrenheit cancels with the degrees Fahrenheit, and you should be able to see that your square inches here cancels with the per square inches that are built into KSI, just leaving you with units of kips, which makes sense because this is a force. So finally, our final answer is going to be stress equals force divided by area. So we're going to say 9.95 kips divided by the cross-section area of that rod, which was 2 inches by 1 inch, which of course is 2 square inches, and that gives us about 4.98 KSI as the stress due to thermal effects. So hopefully you found this example helpful to you. If you like this example, check out some other videos, and please make sure to hit like and subscribe. Thanks for watching.